So in today's lecture we shall just give an introduction to state space representation and state space. First question, why we need to study state space analysis and design of control techniques. You have already learned how to design controllers using transfer functions, and now you are quite expert in those techniques. So why do we need to study this new technique to analyze and design control systems? So it has multiple advantages. Firstly, multiple input and multi-output systems can be easily handled. With the transfer function approach that we studied earlier, most of our studies were focused to systems which had single input and single output. Of course, we can extend that approaches to multi-input, multi-output systems. However, that extension becomes a little bit difficult. Here in the state space analysis, handling multiple input and multi-output systems is the same as handling of single input and single output systems. We call this MIMO system, and single input single output systems are called CISO systems. Another advantage of this state space analysis and design is that nonlinear systems can be easily described by state equations. You remember that transfer functions were these are only for linear systems. We cannot write a transfer function of a nonlinear system. However, this state space representation is equally applicable to nonlinear systems as well. Furthermore, time varying systems can be handled with this approach, and one of major advantages is that these techniques are favorable to modern computers. So therefore these are extensively studied. What is state space? We shall be analyzing and designing control systems in state space. So what is actually state space? To address this question, we first talk about state variables. So what are state variables? So I have written a long statement over here. We shall split this statement into parts, and we shall talk about everything. I read it from here, first line: the smallest set of system variables which completely determine the future value of all system variables. I have omitted this intermediate sentence. So the smallest set of system variables which completely determine future value of system variables. And there is some additional statement. To be able to describe the future behavior of system variables, we need to know the value of state variables at initial time, and we also need to have information of the input signal to the system, and we need some additional equations which are dynamic equations, and these equations we shall call them state equations. Let's elaborate this point with the help of some system. This is an electrical circuit, a simple electrical circuit. How many variables are there in this circuit? So one variable is this current. Current is a variable that depends upon the input voltage. This is a variable. Another variable is voltage across this resistor. Another variable is voltage across this inductor. These are variables. This R and L, these are called system parameters. These are not variables, these are called system parameters. Variables are the current, the voltage across this resistor, and this voltage across this inductor. These are variables. And this voltage signal, we call it input signal. So this thing is now clear, system variables. Now there is another keyword over here, equations describing the dynamics. So we have already learned how to obtain equations which describe the dynamics of this system. We have learned mathematical modeling of electrical circuits, and with the mathematical modeling we can obtain a dynamic equation which describes this system. And that is very easily obtained by applying KVL, for example. So by application of KVL, we have this thing: voltage across this inductor plus voltage across this resistor that is sum of these voltages, that is equal to the applied voltage. That is very simple and you already know that. We can also rewrite this equation in this particular form. Simply bring this term to the right hand side and divide the entire equation with L. So di by dt is equal to minus R by L I plus 1 by L V. So this is a dynamic equation, and it describes the system, and this dynamic equation is called state equation. What is state equation? State equation, first order differential equation in terms of the state variables describing the dynamics of the system. So this equation is called state equation. State equation is a dynamic equation which is written in terms of system variables. We can easily find the solution to this differential equation. You remember the procedure. This is the solution. How did we obtain it? That is very simple for this differential equation, this one as well. How do you solve it? First you find the solution to the homogeneous part, and to solve this homogeneous equation, what do you do is you write the characteristic equation that is written over here and find this lambda, and then you have this kind of solution. How to find the forced solution of this equation? How do you do that? भूल चुके हैं सारी बातें differential equations की. तो you have this constant input and you assume some constant solution and then substitute this solution into this equation over here. That is the procedure. So derivative of this constant with respect to time is 0, so that gives you k to be equal to 1 over r. So this is the solution, forced solution, and this is the homogeneous solution. What is overall solution? Sum of the two solutions. So that is the solution, and if you are provided with some initial conditions, then you can you can determine these constants. You can determine these constants. I of 0 is the initial condition. We have simply substituted it over here, and then this at t equal to 0, this term is simply C1, and this is 1 over r, that is written over here, and that gives you C1 equal to this thing, and that is the overall solution is given by this expression, which is rewritten over here. So that you already know how to find the solution to first order differential equations. So this current is a state variable. Why? Because we can write all other variables in terms of this variable. All other variables can be written in terms of this variable. Therefore, this variable current is the state variable. How we can write other variables in terms of this variable? We see that the voltage across this resistor VR, this variable, is equal to this thing. That is that you already know. And what is voltage across this inductor? That is again written in terms of the same variable. So this concept of state variables is clear. State variables are states is the smallest set of system variables which completely describe other system variables, and for that purpose we also need some additional dynamic equations which are called state equations. So this is state equation, I is state variable, and these are other variables, and these are also called the output equations. And output equation, what is output equation? The algebraic equations. These are algebraic equations. There is no derivative involved over here. These are simple algebraic equations. The algebraic equations that express the output variables of the system as linear combination of state variables and inputs. So this thing is clear. Any question regarding this discussion, since this is a slightly new thing? So state variables, state equations, that is clear. We elaborate it with the help of one more example. Here is another electrical circuit, and now you can easily identify system variables. This signal is the input variable. What are system variables? The current in this loop is a system variable. Uh, so this voltage across this resistor, voltage across this inductor, voltage across capacitor, these are system variables. So now, can we write all system variables as a simple scalar multiple of I of t? Can we write all system variables in terms of this variable I of t as scalar multiple? Yes. How many yes and how many no? Is there any no? For example, how would you write this voltage across this inductor as scalar multiple of this current? That is not scalar multiple, that is you are taking some derivative. So here in this particular system, you cannot write all system variables as simple scalar multiple of this current. This voltage, likewise this voltage, this cannot be obtained by simply multiplying this current by a simple scalar. This can, of course, we can write VR as a scalar multiple of this current. It means that in this system, state variables should be more than one. We cannot write all variables in terms of this variable. State variable is the minimum set which completely describes all other system variables. So here some system variables cannot be represented in terms of this I of t. So therefore this is not the complete set of state variables. So what do you think, can we obtain all other variables in terms of, for example, current and this charge? So the answer is yes, we can write all system variables in terms of these two variables. So for example, voltage across resistor, that is simply R multiplied by I, a scalar multiple of this state variable. What is Vc? Vc is equal to 1 over C multiplied by Q of t, again a scalar multiple of this state this variable. And what is VL? VL is again obtained by simply obtaining linear combination of these variables I, Q and the input. So it means that these two I and Q, this is the minimum set, smallest set of system variables which entirely describe all other system variables. Therefore these two are state variables. And how do we obtain state equations? We have already learnt. So this question is now we have answered. How many states in the systems? There are 2 states in this particular system. And state equations, we have already learnt how to obtain mathematical model for this system. You can simply apply KVL, and by the application of KVL you have this equation. Voltage across this inductor, voltage across a resistor plus voltage across capacitor, sum of these voltages, that is equal to the applied voltage. But what are state equations? State equations were first order differential equation. This is not a differential equation, this is an differential integral equation. There is a derivative term, there is an integral term. So this is not a first order differential equation. We would like to somehow convert it into first order differential equation. So if we substitute I to be equal to what is I? I is equal to rate of change of charge. So we have replaced I with Q, so with dq by dt. So here we have L d square q by dt square, and this I is replaced with dq by dt, and this the derivative replaced over here, that is cancelled out with this integral, and we have 1 over c q equal to v. So again, although we have get rid of this integral term, but still we have second order differential equation. This is not a first order differential equation, and state equations are first order differential equations. We would like to split it in 2 first order differential equations. How we do that? We know that dq by dt, that is equal to current I, and what is di by dt? Di by dt, by simply bringing this term to the right hand side, that is equal to minus r over li, this term, and 1 over LC q, this integral, that is equal to q, and plus this 1 over LV. So basically what we have done is we have converted this second order differential equation into two first order differential equations, and these two first order differential equations, these are called state equations. In previous case there was one state variable, one state equation. Here we have two state variables I and q and two state equations. The derivative of first state variable, and on the right hand side no derivative, only a simple linear combination of state variables, and the derivative of second state variable, and on the right hand side we have a linear combination of the state variables. So these are state equations and these are two state variables, and here these are the output equations. We have written other variables in terms of simple linear combination of these state variables and input. So these equations, no differential derivative is involved over here. These equations are called output equations. So here number of states in a system is equal to number of energy storing elements. Here in this particular system, this inductor is energy storing element, it stores energy. Capacitor is energy storing element. There are two energy storing elements, therefore number of states in this system is equal to 2. In previous example there was only one energy storing element, therefore there was only one state, and that is true for any physical process. You can also talk about mechanical systems. If in mechanical system what are energy storing elements? Damper is not energy storing element. Damper dissipates energy, that is equivalent to resistor in electrical circuits. So in mechanical systems spring and mass, these are energy storing elements. Here is one very important point: choice of state variables is not unique. In previous case slide we had taken two state variables. What were those state variables? I and q, these were state variables, but that is not the only choice for state variables. What we had done on previous slide, we had taken two variables I and q and written all other variables in terms of those two variables, but this is not the only choice. You can, for example, in this particular system, again we take the same system, voltage across this resistor and voltage across capacitor can also be taken as state variables. We show that all other variables can be written in terms of these two variables, so that is easy to show. For example, the other variable current, that can be written in terms of these variables. Current is equal to 1 over R into VR, that is obvious from over here, and likewise voltage across this inductor, that is equal to this thing. So what we have done is that in the previous slide we had taken current and charge as state variables and written all other variables in terms of those two variables. Over here what we have done is we have taken this VR and VC as state variables, and we have written all other variables in terms of, when we say in terms of, we mean as a linear combination of the state variables and the input signal. And therefore we can also write the state equations in terms of new state variables. These are the state equations which we had written on previous slides, but these state equations are in terms of previously defined state variables. We can write these state equations in terms of these state variables as well. So that is simple. For example, what is dvr by dt? That is simply given by this relation. You can easily verify it. That is done over here. So what is conclusion of this slide? State space representation and state variables is not unique. You can have a different choice of state variables as well. So now the question is, can we take any two variables as state variables? What do you think? We have learned that state space representation and choice of state variables is not unique. So now on the previous slide we had taken two state variables. On this slide we have taken two other state variables. So we know that for this particular system there are two state variables, but now the question is whether any two variables can be taken as state variables. Right. So if that set completely defines the system, that is all other variables can be written in terms of those variables, then yes, but otherwise no. Any two variables cannot be in general taken as state variables. For example, you cannot take this I of t and Vr as state variables. Why? Because all other variables cannot be written in terms of these variables. So here is our rule: state variables should be linearly independent from each other. What do we mean by linear independence? For example, this I and Vr, these are not linearly independent. How we say that these are not linearly independent? This Vr can be obtained by a simple scalar multiple of this current. So these two variables are not linearly independent. State variables should be linearly independent. Sometimes it is more convenient to represent state equations and output equations in the form of matrix. So here we have state equations and the output equation of the system described on the previous slide. We write it in matrix form. How we can write it in matrix form? That is quite simple. You can verify that if you multiply these things, again we get the same expression. For example, 0 multiplied by q plus 1 multiplied by I and 0 multiplied by v. So that is the first equation, and here is the second equation. And VL is equal to this thing is written over here, q multiplied by minus 1 over c and minus r multiplied by I, that is this output equation. So state equations and output equation written in matrix form. And generally we represent state variables with this symbol x1 and x2. This is just convention, not necessary, but convention. We represent the state variables, denote the state variables with x1 and x2. So what we have done is we have named q equal to x1, I, we have named I to be equal to x2. This what is meaning of this symbol? This mean not approximately, this means we have defined it, we have named it. We have named q to be equal to x1, I to be equal to x2. X is equal to x1, x2, and this matrix is this one. What is this thing? This is vector x. This is vector x written over here, and we call this matrix B, and this input, we denote the input with u. And likewise, if we look at the output equation, it is convention, we write the output, we represent the output with y, and we name this matrix as C. So do not confuse this C with this C. This is the name of this matrix. And what is this C? This is capacitance of the capacitor. So these two C's are completely different. So C multiplied by this vector, which is x, and some matrix. In general, here will be some matrix, but in this particular case it is some scalar. Scalar is 1 multiplied by v. So here the multiplied we multiply it by a scalar, but in general it will be a matrix. so that is denoted by D, and the input to the system is denoted by with U. So this particular representation is called state space representation, and this vector x is called state vector. This vector x is state vector which contains the state variables. Q is a state variable, I is a state variable, and we have named these variables differently. We have called them x1 and x2. So this vector is called state vector. U is the input vector. This in this case, this V, there was only one input to this system, that is voltage, but that is not always the case. You may have multiple inputs to the system. So in general, this will be a vector, but over here it is a scalar. So we have written the general thing. U is the input vector, Y is the output vector, and this matrix A, this matrix over here, this one, that is called system matrix. This matrix over here, which is being multiplied with the input to the system, that is called input matrix. This matrix which is being multiplied with state variables over here, that is called the output matrix, and the thing which is multiplied over here and denoted by D, that is called feed forward matrix. And this representation is the state space representation. This representation, this one is the state space representation. So I think all these concepts are clear. There is one question. X bar हमने कहाँ पे लिखा है? X dot, right. So x dot represents the derivative of x with respect to time. Here, what is this? This vector we have named it as x, and here is derivative of the same vector. Derivative of the same vector with respect to time. So that is the derivative of the state variables, and this particular representation is called state space representation.